Hi students, good morning. I hope you are all safe and healthy. I am Venkat, AS Physics course instructor. Welcome to week 11. In week 11, we are going to discuss on stationary waves. So you have learning objectives. You can pause the video and copy the learning objectives in your copybook. And you have also got homework, end of chapter questions, page number 219 to 221. Questions 1 to 6. So it will be easy for you to do this. And let us start with the stationary waves. So far, you have learned about progressive waves, and you know that they start from a source and travel outwards, transferring energy from one place to another. A second important class of waves is a stationary waves, and this can be observed as follows. For example, if you use a long spring or a slinky spring, a long rope or a piece of rubber tubing can also do. Lay it on the floor and fix one end firmly, move the other end from side to side so that transverse waves travel along the length of the spring or the string and reflect off the fixed end. As they reflect off the fixed end, if you adjust the frequency of the shaking, you should be able to achieve a stable pattern like one of those seen in the figure. And the frequency, if you alter the frequency in order to achieve one of the other patterns, you should notice that you have to move the end of the spring with just the right frequency to get one of these interesting patterns. The pattern disappears when the frequency of the shaking of the free end of the spring is slightly increased or decreased. Standing waves on elastic string. First, we'll observe this. It's a video. You can see that the string is attached to a fixed end, and then the free end, the other end, is attached to a vibrator. So if you adjust the frequency of the vibrator, the string will start vibrating. As they start vibrating, you will see that, or we will observe the standing waves on a string. And you will be able to see from this a standing wave is achieved. One of the pattern of standing wave is achieved. And this point, which is called a node, where there is no motion and where there is a maximum amplitude or maximum vibration, that point is called antinode. And if you adjust the frequency, the pattern gets changed. You will see a different pattern now since the frequency is altered. Now you can see that the number of nodes and the antinodes also increased. As you adjust the frequency, the number of nodes and antinodes is also increased. And we can count the number of nodes and antinodes in this pattern. So there are four nodes in this pattern, 4 nodes and 3 antinodes. And always remember that at the ends of the string, it is node point. That is where there is no motion of the string. And in between, you can see that, or you can observe that the nodes, antinodes and the nodes. And this point is called again a node point, where there is no motion of the string. And this point, which is called a antinode, where you can observe maximum amplitude of the stationary wave. Now we have nodes and antinodes. So we can see that, or we have observed is a stationary wave on the long string. There are points along the string that remain motionless. That's what we have observed, while points on other side are oscillating with the greatest amplitude. The points that do not move are called the nodes, and the points where the string oscillates with the maximum amplitude are called the antinodes. At the same time, it is clear that the wave profile is not traveling along the length of the string. Hence, we call it a stationary wave or a standing wave. We normally represent a stationary wave by drawing the shape of the string in its two extreme positions. The string appears as a series of loops separated by nodes. And in this diagram, point A is moving downwards. That's what you are able to see from the figure. Point A is moving downwards. At the same time, point B in the next loop is moving upwards. The phase difference between points A and B, that is equal to 180 degree. And hence, the sections of the string in adjacent loops are always moving in antiphase. They are half a cycle out of phase with each other. So this is very important to note that the sections of string in adjacent loops are always moving in antiphase. They are half a cycle out of phase with each other. Then we have a formation of wave. So to form a stationary wave, so it's very important to note that to form a stationary wave, we require two progressive waves of the same amplitude and wavelength traveling in opposite directions. They superimpose and they form a standing wave. In this figure, a formation of a stationary wave along a long string is illustrated, and at time t equal to 0, the progressive waves traveling to the left and right are in phase with each other. The waves combine constructively, giving an amplitude twice that of each wave. After a time equal to 1/4 of a period, that is t is equal to t capital T over 4, each wave has traveled a distance of 1/4 of a wavelength to the right or left. Consequently, the two waves are in antiphase and the phase difference is equal to 180 degree. The waves combine destructively, giving zero displacement. After a time equal to 1/2 of a period, that is time small t is equal to capital T over t, the two waves are back in phase again. They once again combine constructively, giving a maximum amplitude. After a time equal to the 3/4 of a period, that is time t is equal to 3t over 4, that is 3 capital T over 4, where capital T is the time period. The waves are in again antiphase. They combine destructively with the resultant waves showing zero displacement. After a time equal to one whole period, that is small t is equal to capital T, the waves combine constructively. The profile of the string is as it was at time t equal to 0. That is what you are able to see from this figure. Next, we have the differences between progressive wave and stationary waves. Some of the points are noted here, and it is worth noting that a stationary wave does not travel and therefore has no speed. It does not transfer energy between 2 points like the progressive wave. And in this figure shows some of the key features of a progressive wave and its stationary wave. And you will be able to see that the differences between the progressive wave and the stationary wave. In case of amplitude, for a progressive wave, all particles will have the same amplitude, but stationary wave, the amplitudes are different. The crest and trough of move along the string, but whereas in the case of stationary wave, the nodes and the antinodes, they do not move along with the wave profile. And particles of string attains maximum displacement at different times. And for the stationary wave, the particles of the string attains maximum displacement at the same time. And there are only certain frequencies of stationary waves possible. And you should also notice that the wavelength for the stationary wave and the progressive wave are the same, because we use two progressive waves of same frequency and same amplitude to form a stationary wave, same wavelength. And frequency is also the same. And the speed for a progressive wave is v, because it has a velocity, but for a stationary wave it does not travel along. Therefore for a speed for a stationary wave is 0. So these are the important points. You have to keep this in your mind when you write the differences between the progressive wave and the stationary waves. Stationary waves and musical instruments. The production of different notes by musical instruments often depends on the creation of stationary waves. That's what we are able to see from the figure. For a string instrument such as a guitar, the two ends of a string are fixed. So notes must be established at these points because the two ends of the string is fixed. So notes must be established at these 2 points. When the string is plucked halfway along its length, it vibrates with an antinode at its midpoint. This is known as the fundamental mode of vibration of the string. The fundamental frequency is the minimum frequency of a standing wave for a given system or arrangement. And then similarly, the air column inside a wind instrument is caused to vibrate by blowing, and the note is heard depends on a stationary wave being established. By changing the length of the air column, as in a trombone, the note can be changed. Alternatively, holes can be uncovered so that the air can vibrate more freely, giving a different pattern of notes and antinodes. In practice, the sounds that are produced are made up of several different stationary waves having different patterns of notes and antinodes. For example, a guitar string may vibrate with two antinodes along its length. This gives a note having twice the frequency of the fundamental and is described as a harmonic of the fundamental. The musician's skill is in stimulating the string or air column to produce a desired mixture of frequencies. The frequency of a harmonic is always multiple of the fundamental frequency, and I'm going to show you the diagram. The possible stationary waves for an air column closed at one end. So here, some of the possible stationary waves for an air column closed at one end. So this is the air column closed at one end, and you will be able to see from this the fundamental mode of frequency that is given by f naught. So to achieve the fundamental mode of frequency, the length should be adjusted. So the length of the air column should be equal to 1/4 of a wavelength, that is equal to lambda over 4. And for the closed organ pipe, that is one end of the organ pipe is closed, the frequency of each harmonic is an odd multiple of the fundamental frequency f naught. If it is odd multiple of the fundamental frequency f naught, the next frequency can be achieved at 3 f naught, and therefore in the length of the air column should be equal to 3 lambda over 4. And for the next frequency, again the odd multiple, so therefore the next fundamental frequency, the third harmonic, will be equal to 5 lambda by 4. And in the same way, we can do for the possible standing waves for a fixed string of length L. And you will be able to see from this figure the fundamental frequency of the string for a string which is producing a standing wave that is equal to f naught, and the two fixed points, there will be these called the node points, and the distance between the two consecutive nodes, that is equal to half a wavelength. Therefore this lambda is equal to 2L. And in the case of standing waves for a fixed strength of length L, the frequency of the harmonics is a multiple of the fundamental frequency f naught. Therefore the second harmonic will be 2 times of the fundamental frequency, that is f naught, 2 f naught. And for the third harmonic, it's equal to 3 times of f naught. And it is also important to note that if in the second harmonic, how many notes and antinodes are formed. And you will be able to see from this for a string, there are 3 notes and 2 antinodes. And for the third harmonic, again, how many notes and antinodes are formed. So for the third harmonic, again, 4 notes and 3 antinodes. Whereas in the case of possible standing waves for a closed organ pipe, you will be able to see that for the fundamental mode of frequency, so there is only 1 antinode and 1 node. And for the second harmonic, there are 2 antinodes and 2 nodes. And for the third harmonic, definitely it will be 3 antinodes and 3 nodes. So this you have to keep in your mind, because this will be very useful in problem solving. Now we have problem solving. I will share you a PDF, and it is a past paper question. You can see from the document, that is to state two features of a stationary wave that distinguish it from a progressive wave. And it is noted here, the nodes and antinodes do not move along the string for a stationary wave. The crust and troughs do move along it for a progressive wave. And also note that progressive wave, all points have the same amplitude, but for a stationary wave, the amplitude of vibration varies with the position along the string, and it is zero at node point. And we have also part B, a long tube is open at one end. It is closed at the other end by means of a piston that can be moved along the tube, as shown in figure. And here, a loudspeaker producing a sound of frequency 550 hertz is held near the open end of the tube. The piston is moved along the tube and a loud sound is heard when the distance L between the piston and the open end of the tube is 45 centimeter. The speed of the sound in the tube is given as 330 meter per second. Show that the wavelength of the sound in the tube is 60 centimeter. Since length L is equal to 45 centimeter, and it is also given the velocity of sound 330 meter per second, we can use the wave equation to find the lambda, that's the wavelength of the sound used by the loudspeaker, that is equal to 330 divided by 550, we get 0.6 meter, that is equal to 60 centimeter. And we have also got as a second part, on figure 4.1, mark all the positions along the tube of the displacement nodes, label these with the letter N. The displacement antinodes, label these with the letter A. Now we'll go to the figure. For example, if you place a loudspeaker in front of a closed organ pipe, which is one end of the organ pipe is closed, and we have learned that the first mode of frequency, or the fundamental mode of frequency, that is equal to when length L is equal to 1/4 of wavelength, and we have calculated the wavelength that is equal to 60 centimeter. Since 1/4 of wavelength that is equal to 15 centimeter, so we have to adjust the piston to 15 centimeter to hear the first loud sound. Then we also note that the fundamental mode of frequency, the frequency of modes of frequency of vibration in the case of organ pipe closed at one end, in the ratio of 1:3:5. Therefore, the next mode of frequency will be heard at 3 times of its 1/4 of a wavelength. So 3/4 of a wavelength. And 1/4 of a wavelength, just now we have calculated, that is equal to 15 centimeter. Therefore, 3/4 of a wavelength, that is equal to 45 centimeter. And the length of the air column is also adjusted to 45 centimeter because the piston has moved to 45 centimeter. Now we will be able to observe the second loud sound when the speaker is in front of the closed organ pipe. Now, how many nodes and how many antinodes? That's also we have learned. If it is a closed organ pipe, if 3/4 of a wavelength, therefore how many wavelengths or how many nodes and antinodes will be formed between the ends of the tube? That is equal to 2 antinodes and 2 nodes. That's what you are able to see from here. We can also check I told you that since L is equal to 45 centimeter, there are 3/4 of a wavelength. So 3/4 of a wavelength, that is equal to 45 centimeter. So 1/4 of a wavelength, that is equal to 15 centimeter. And we also have learned that the distance between antinode and node, that is equal to 1/4 of a wavelength. And again, distance between node and antinode, 1/4, that is equal to 30 centimeter. And the distance between antinode and node, again 15 centimeter, giving a total of 45 centimeter. So now it's very clear that there are 2 antinodes and 2 nodes in between the length of the tube. So we can write our answer here, that is the displacement nodes equal to 2 and the displacement antinodes, that is equal to 2. And we have also marked this with the letter A on the figure. So this is the point where you see there is no vibration, that is the node point, where you see maximum amplitude, that is anti-node. And this is again a node point where there is no vibration, and this is again maximum amplitude where you see the anti-node. So we have got part C also. The frequency of the sound produced by the loudspeaker in B is gradually reduced. Determine the lowest frequency at which a loud sound will be produced in the tube of length L is equal to 45 centimeter. So here the length of the tube is not adjusted, just the frequency has been adjusted, therefore the wavelength will be changed. So now we calculate the new wavelength using the expression that is L is equal to lambda over 4, because the F minimum or the fundamental frequency, to calculate fundamental frequency, the L is equal to lambda over 4. Therefore, lambda is equal to 45 times 4, that is equal to 180 centimeter. And we also know that the speed of the sound in air, that is equal to 330 meter per second. Now we can calculate what is the lowest frequency, that is F minimum, that is equal to 330, which is the velocity divided by lambda, that is equal to 180 centimeter. So converting centimeter to meter, multiplying with the 10 to the power of negative 2, we get the frequency minimum, that is equal to 183.3 hertz. And it is also important to note that some of the differences between stationary waves and a progressive wave, between adjacent nodes, all points of the stationary wave vibrate in phase. All particles of the string are at their maximum displacement at the same instant. This is for a stationary wave. For a progressive wave, the pace varies continuously along the wave. All neighboring points along the wave are out of phase with each other. There are only certain frequencies of stationary waves possible. That is what we have seen for a closed organ pipe which is one end closed. That is the ratio, the frequency of the modes of frequency of vibration in the ratio 1:3:5. For a string, it is 1:2:3. In the case of stationary waves, in the case of progressive waves, all frequencies are possible. The allowed frequencies for a stationary wave depend on the length of the string and the speed of the progressive wave that form the stationary waves. So these are the important points we have to keep in our mind when writing the differences between the progressive wave and the stationary wave. And that's all we have in this chapter. I will meet you with some of the past paper questions in the next video. Thank you. Keep learning and keep doing good.